Okay guys, Timmy coming at you here. And today what I'm going to do, believe it or not, is I'm going to try to put together everything that we've gone over this semester in like 15 minutes. Alright, let's see if I can do it. First of all, if you've ever seen these little bunny episodes where they take a movie and they make it into like a 30-second clip, the entire movie, that's what I'm going to do with this entire class. So watch the little bunnies. Ready? I don't have sound on it, so what are you gonna do? Oh, just so you know, I'm working with this guy trying to revolutionize my swing. But anyways. Boom. That's the bunnies in 30 seconds. Titanic. Alright, here we go. Alright. Watch. Watch. Number one, contracting muscles require ATP, right? And then contracting muscles produce more ADP. And if you recall, ADP, the buildup of ADP inside a cell, in this case a muscle cell, it's the biggest stimulator of metabolism, right? So aerobic metabolism, anaerobic metabolism are going to speed up. And as you know, aerobic metabolism requires oxygen. Where do you get that oxygen from? You get it from the blood. How do you get more arterial blood there? Well, you got to remember that byproducts of metabolism are massive arterial vasodilators, right? And arterial blood always takes the path of least resistance. What's the best way to transport oxygen? Bound to the iron on hemoglobin. Is exercise stressful? Yup. So you're going to get the release of epinephrine from the adrenal medulla. Alright, so here we go. Let's start out at the muscle cell. So you're sitting on your fatty ass and you decide to get up and you decide to go run. In order to run, you have to contract more muscle. In order to bind the myosin head to the active site on actin, right, you need ATP. When you use ATP, you break it down to ADP plus a phosphate, and then ADP starts building up. What's the most powerful stimulator of the enzymes of metabolism? The buildup of ADP inside the cell. So what happens, right? We know this. You start building up more heat, increase PCO2, drop in PO2, and increase hydrogen ions. What do those do to the arteries and arterioles that are supplying your legs? They are massive arterial vasodilators, right? So the arteries that are supplying the metabolically active arms and legs while you're running are going to produce more byproducts of metabolism. They're at least temporarily going to lack oxygen, and that's going to cause the arteries to dilate. And when the arteries dilate, there's less resistance compared to arteries in the non-metabolically active parts. That's also the effect of epinephrine. If you remember, epi is a massive arterial vasoconstrictor, right? So it's going to constrict the non-essential parts of your body so that you can send that nice oxygenated blood to the parts of the body that you need to get up and start running. Now, because those arterial vasodilators, right, you're going to need more blood. How do you get more blood? Well, guess what? You're getting up and running, right? So where do you store a lot of extravenous blood? In the veins of your legs. So now you're contracting more muscle. What's that going to do to the amount of venous blood coming back to the right side of the heart? It's going to increase it. And as we know, anytime you increase the amount of venous blood back to the right side of the heart, you're going to stretch the right side of the heart. And when you stretch it, you line up the actin and myosin. Watch it. And when you line up the actin and myosin better, you increase the force of contraction. And if you increase the force of contraction, you increase stroke volume and you increase systolic blood pressure. Now there's more blood going to the lungs. And we learned that the amount of blood pumped by the right heart is equal to the amount of blood pumped by the left heart. So now you got more blood in the left side of the heart. What do you do to the left side of the heart? You stretch it. You increase the force of contraction because you've lined up the actin and myosin, and you increase systolic blood pressure. Now you're sending more blood to your muscle cells, right? Under higher pressure. And we know that exercise is stressful, and epinephrine increases your heart rate. So the combination of increased heart rate and increased stroke volume, we know that cardiac output is heart rate times stroke volume. So blood flow, cardiac output goes up. Yep, it does. Now you're going to send all that oxygenated blood to the muscles where you need it. Watch it. What are you going to start building up in the blood at the level of your muscle cells? Well, you got it. You're going to start building up the byproducts, but more importantly, you're going to be increasing the PCO2. Does breathing increase immediately upon the start of exercise? The answer is no. But now you're sending more blood with a higher CO2 concentration to the lungs, but you haven't increased breathing. That means, excuse me, when gases are exchanged at the level of the pulmonary capillary and the alveoli, you're not going to be able to get rid of all that extra CO2. What happens? CO2 starts building up in the arterial blood. It will diffuse from the arterial blood into the cerebrospinal fluid, combined with water, form carbonic acid. Carbonic acid dissociates into hydrogen ions and bicarbonate ions, and the hydrogen ions directly stimulate the medulla to send a signal down the phrenic nerve to begin to contract the diaphragm and the accessory muscles of breathing, so you can ventilate more alveoli, get more oxygen in, and get rid of more CO2. Now you got more oxygen bound to the iron on hemoglobin. Where's the vast majority of that oxygenated blood going to go? It's going to go the path of least resistance created by the byproducts of metabolism. We also, also know that hemoglobin is a protein, and that proteins are temperature and pH sensitive. So as those red blood cells matriculate down through the path of least resistance to the metabolically active arms and legs, what's going to happen to that red blood cell? Well, it's going to be exposed to a higher temperature, a higher PCO2, a lower PO2, and a drop in pH, an increased amount of hydrogen ions. And we know from the study of the respiratory system and the oxyhemoglobin dissociation curve that it will cause oxygen to fall off the iron or dissociate and sit at the end of the electron transport chain. Now, all that venous blood's going to come back to the right side of the heart? Oh yes, it does. And now that red blood cell with no oxygen or very little oxygen bound to it, it's going to go to the lungs. But what are the conditions in the lungs? Well, there's increased PO2 in the lungs, right? There's decreased PCO2 because you're getting rid of it. And we know that CO2 is an acid. So that's going to cause oxygen to want to bind to the iron on hemoglobin. And that, ladies and gentlemen, is putting it all together. Watch it. When a muscle cell is muscling, when it's contracting, what fuel is it going to use? It's going to use the fuel that's most readily available, right? We also know that muscles store glycogen, which is glucose chemically bonded together and stored with water. So it will use some of its glycogen stores, and it will use some glucose or fat from the blood. One thing I didn't tell you, but now I will. Contracting muscle does not need insulin to get glucose from the blood into the cell. Boom. The contracting muscle actually activates a protein called the GLUT4 transport protein that allows glucose to go from the blood into the muscle cell when it's contracting. Now, watch. As you start exercising, contracting muscles produce heat. So your body temperature is going to go up. That's going to be detected by the hypothalamus. One of the ways or the best way to dissipate heat is through the evaporation of sweat. So you will begin to sweat. Also, arteries will dilate to the skin to try to radiate that extra heat in an attempt to maintain your core body temperature. Yep. So I don't know if that was 30 seconds. Oh, okay. It was 10 minutes. But I put the whole class together, literally, in less than 10 minutes. All right. Nice. Okay, be safe out there.